Hello everyone, my name is Yoojin Lee. I would like to talk about our recent paper titled Establishing Intra and Inter-Vendor Reproducibility of T1 Relaxation Time Measurement with 3T MRI. This work has been done mainly in University of Zurich in collaboration with UCL in London and Lausanne University Hospital. T1 relaxation time is an inherent quantitative property of tissue, and it depends on several tissue properties such as macromolecular and iron concentrations. Since myelin has a high macromolecular content, T1 value is often used as a biomarker of myelination. Having other quantitative values, for example T2 relaxation time, magnetization transfer rate, and proton density, helps characterize the underlying tissue in more details using biophysical modeling. The motivation behind using quantitative measures rather than T1 weighted image or T2 weighted image is the previous indication that it is more reproducible across site, scanner manufacturers, scanner models, and time points, which is particularly attractive for multi-center and longitudinal studies. However, we found out that the quantitative mapping does not always produce reproducible results, especially for the case where the multiple scanners from different vendors are involved. In this paper, we want to report such cases. Among many other quantitative T1 mapping methods, we chose this variable flip angle approach because it is widely used, extensively optimized, and this analytical framework is available for the estimation of voxel-wise T1 values. This approach requires 3 input images to estimate T1 values. 2 spoiled gradient echo images acquired with 2 different flip angles, and 1 B1 map to correct for the transmit B1 inhomogeneities. If you plug in these 3 images into this equation, then you get the quantitative T1 map. This method is well established on the Siemens scanner, so we implemented this T1 mapping sequence on our local Philips scanner and compared it to the one from the Siemens scanner. Here you see the 2 different RO maps, which is just an inverse of T1, on the same subject, acquired on the Siemens scanner and the Philips scanner. If you display them in grayscale, as people normally do, then you hardly see any differences between them. But if you display them in color map, you can see that so-called quantitative T1 values are different, although the imaging object stayed the same. This prompted our study on the reproducibility across scanners. So we started searching for the reasons for the difference. And the first culprit we found was B1 maps. If you repeatedly measure B1 maps with the same sequence, you get the different B1 maps. And this variability in B1 map propagates into T1 map. For example, in axial slice, you get the high value at the center, but it gets more asymmetric in second and third dataset. And you can see the same effect on the R1 maps. And you have this hole in the third B1 map, and this remains in the corresponding RO map here. So we optimized our B1 mapping sequence by increasing the spoiler gradients, and we were able to acquire a highly reproducible B1 map and accordingly highly reproducible T1 map as well. For the detailed information, please check out our previous paper. Once we optimized the B1 transmit field map, we moved on to investigate the reproducibility of the entire T1 mapping protocol. We performed 3 studies. Let's start with the first study where we established the inter-vendor reproducibility and intra-scanner reproducibility. In this study, 7 participants were scanned twice on 2 scanners from the different manufacturers. One was 3T Siemens Trio system and the other was 3T Philips Achieva system. We tried our best to match the acquisition parameters for the spoiled gradient echo sequence, but we were not able to fully harmonize all the parameters. For example, different parallel imaging methods are implemented on 2 scanners from different vendors. The Siemens system used Grappa and the Philips system used Sense. And because the 32-channel head coil was used on Siemens scanner, whereas the 8-channel head coil was used on Philips scanner, we were not able to use the higher acceleration factors than 2 on Philips scanner. Instead, we used partial Fourier to match the acquisition duration. Here are the results for the first study. The images shown here are T1 variability maps calculated by dividing the difference between 2 T1 maps by the mean of 2 T1 maps multiplied by 100. The image on the left is the T1 variability map from the test-retest T1 maps acquired on Siemens scanner. And the image in the middle is the T1 variability map on the Philips scanner. The Siemens scanner had noisier test-retest T1 variability map, whereas the Philips scanner had the low spatial frequency variation in the T1 variability map. The image on the right is the inter-vendor variability map, where I took the first T1 map from Siemens scanner and the first T1 map from the Philips scanner and calculated the variability between them. You can see that intra-scanner variability has values around 0, whereas the inter-vendor variability has a systematic bias around 10%. Here you see the histogram of the T1 values itself and the T1 variability for 4 different ROIs. Different colors represent 7 different participants. Here the solid lines are for the T1 values from Siemens scanner and the dashed lines are for the T1 values from Philips scanner. You can see that the histograms from different participants but from the same scanner are quite close to each other, but the histograms from 2 different vendors are quite separated from each other. You can see the same in the histogram of T1 variabilities. Intra-scanner variability for both scanners, shown as thin solid lines and thin dashed lines, were approximately 0-centered for all ROIs and all participants, having the averaged median values around zeros, as you can see in these red numbers. But the median of the inter-vendor variability, shown as thick solid lines, was around 10% in white matter, 7.8% in cortical gray matter, 8.6% in subcortical gray matter, and 10% in cerebellum. Let's move on to the second study we performed. In this study, one of the 7 participants was additionally scanned on 4 consecutive days on another 3T Siemens Trio scanner installed at the same site as the first Siemens scanner. With this additional dataset, we evaluated reproducibility across 2 different scanners from the same vendor, as well as the longitudinal reproducibility. These 2 images are the test-retest variability on the first Siemens scanner and the second Siemens scanner. The image on the right is the T1 variability between 2 identical Siemens scanners. You no longer see such big systematic bias as in the T1 variability map between 2 scanners from different vendors. On the right, you see the histograms for the T1 values in 4 different ROIs. different colors represent different ROIs. The histograms from the 4 T1 maps acquired on the second Siemens scanner, shown as the solid lines, are quite similar to each other, indicating the high longitudinal reproducibility. Here, the thin solid lines are the histograms of the test-retest T1 variability on the first Siemens scanner. The dashed lines are the histograms of T1 variability across 4 T1 maps acquired on the second Siemens scanner, and the thick solid lines are the histograms of T1 variability across first and second Siemens scanners with the same model. Again, the intra-scanner variabilities were pretty low, having the median values of near zero, but the median values for T1 variability between two identical Siemens scanners were slightly higher than the T1 variability from the same scanner. In study 3, another participant was scanned additionally on 4 consecutive days on the same Philips Achieva scanner, but after a software upgrade to evaluate the reproducibility across software versions. Again, the test-retest variability of the T1 maps acquired on the same software was low, with the median values near zero, but the T1 maps acquired before and after software upgrades were slightly different. The T1 variability across software versions on the Philips scanner was comparable to the T1 variability across two identical Siemens scanners. It was higher in white matter and cortical gray matter, but lower in subcortical gray matter and cerebellum. But please note that the longitudinal studies were performed only on a single subject, so this reproducibility level should be taken as an indication only. In summary, we observed 8 to 10% bias in T1 values between two vendors, 1 to 2% between two scanners of the same model from the same manufacturer, and 2 to 4% between two software versions on the same scanner. The biggest bias was observed between two vendors. To think about the potential sources of this bias, here we listed the remaining differences between two vendors. First, the main magnetic field strength was slightly different, so the T1 values are expected to be different as well. And different B1 mapping sequences were used on two scanners. Philips scanners offer a product AFI B1 mapping sequence, which is not available on Siemens scanner. So AFI approach was used on the Philips scanner after some optimization to improve the test-retest reproducibility. And on the Siemens scanner, 3D EPI-based approach, which was already implemented and validated on site, was used. It has been shown in this paper that the 3D EPI-based method produces higher B1 estimates than the AFI method, which would result in lower T1 estimates on Siemens scanner. This is in line with our experimental result. And of course, the hardware components such as gradient coil, RF coil, and shimming coils were different. The bias between two vendors could stem from some combination of differences listed here. Harmonizing those aspects listed here across the scanners is important for future efforts to investigate or eliminate the bias. For example, offline reconstruction would enable us to use a common unfolding algorithm. And the same B1 mapping method could be used, and the same head coil could be used. However, note that if all the differences were eliminated, then the two scanners would become exactly the same scanner, and then it's obvious that the bias between two manufacturers would also disappear. So now you might agree that it is impossible to fully harmonize across scanners from different vendors. We have to somehow live with this bias. This brings out the importance of pilot study for multi-center studies. Here I would like to show you how the results presented in our study can be used to optimize the design of the multi-center studies. In the example ROI precentral gyrus, based on the variability in T1 values across the participants, the required sample size was calculated for the effect size of 5%. For the intra-scanner T1 maps, the required sample size was 3 to 5, whereas it was 9 to 19 for the inter-vendor T1 maps. So you have to recruit substantially larger group of people if you want to use two scanners from different vendors. In our case, T1 variability across vendors was dominated by a systematic bias. In this case, it could be partially eliminated before analyzing dataset by subtracting or adding the bias averaged across participants. If you do that, then the required sample size reduced to 2 to 7 in our example. The take-home message from this study is that if the study involves multiple scanners or even the same scanner but different software versions, then the researchers should bear these possible variabilities across scanners in mind and conduct a pilot study to determine the level of reproducibility and use that information to design the full-scale investigation. Thanks for your attention.